Wonderful. Thank you so much for the invitation. I'm really pleased to be here. And that was also just an amazing talk, Alice. I really enjoyed that. And I think seismic waves going through a block of cheese was definitely the highlight of my day. So thank you for that. So yeah, I'm here to kind of ideally provide a little bit of an outside perspective of how machine learning is being used in other fields of kind of physical sciences, in particular in my field of fluid dynamics. Before I jump in, I'm going to acknowledge a number of my excellent co-authors, colleagues, students, postdocs, and this is just kind of a snapshot of the people that I've been working with, fortunate to work with on these topics, merging machine learning and fluids. So I love fluid dynamics. I think this is my applied passion as an engineer, but I want to kind of broaden this out. When I say fluids, all I want you to think about is high-dimensional, nonlinear, multi-scale problem that you want to model, estimate, predict, and control from limited measurements, okay? And that makes this much more general to disease modeling, climate science, neuroscience, pretty much any of those fields that are high-dimensional, nonlinear, multi-scale. I'm going to talk about fluids because that's my passion. And something I really want to point out here is that most of the engineering tasks in my field, so model reduction, going from those millions or billions of degrees of freedom down to the key variables, reduced order modeling, control, sensing, closure, these can all generally be posed as very challenging optimization tasks. And they're challenging, again, because they're high-dimensional, non-linear, non-convex, and this is because of their multi-scale nature in space and time. And so I believe a lot of you kind of on the other side of the screen also share some of these problems. Now, what I love is this perspective, and I'm going to pigeonhole or oversimplify a little bit, that machine learning is this fantastic new and growing set of techniques to build models from data using optimization. So we can start to solve these canonically challenging optimization problems in engineering and in the physical sciences with these emerging data-driven optimization tools that broadly form this umbrella of machine learning. So if you take away one thing, I would say it's this pigeonholing that machine learning is essentially data-driven optimization. So if you have a classic optimization problem, you can oftentimes do better if you have a lot of data nowadays, okay? Now, I talk a lot to executives at Boeing and companies where there's this feeling that machine learning is magic. It's, it's Harry Potter. You wave a wand at a problem and it gets solved. And I think this is really important for us in the physical sciences. We have F equals ma. And so we need to demystify what this machine learning is doing behind the scenes when we apply it to physical systems. And so one of the things that my group really is pushing a lot is this need for interpretable and generalizable machine learning for the physical sciences. And I'm going to go through some vignettes walking you through examples where we're trying to promote interpretability. Now, this is one of those things where trying to define interpretable and generalizable is more trouble than it's worth, and no one will agree with me if I give a definition. So instead, I'm going to give an analogy. I'm going to go back to Newton with the falling apple, where, on Earth, observing this falling apple, he was able to derive this F equals ma. And I would say that is the ultimate interpretable and generalizable model. That's what we want our machine learning techniques to be returning to us, are things much more like F equals ma than a black box neural network with 1 billion free parameters, okay? Because so in the sense of generalizability, this could be learned from a falling apple on Earth, but it still applies to landing, humans on the moon, for example, something that was never seen before. And it's interpretable in the sense that there are only a few key terms in the equation that you can discuss, analyze, interpret. Okay, so that's what we want out of our machine learning solutions, are these kinds of simple models. And this is not just Newton, this has been across the board in science for the last 2,000 years. People have been looking for the simplest explanation that fits your observational data. And in general, mathematically, in the 21st century, we find those models by promoting sparsity, low dimensionality, and those lead to robust, interpretable, and generalizable models. Okay, that was my soapbox. Now I'm going to go into a little bit of detail about how we get these models with sparse optimization and machine learning. Okay, so I want to talk a little bit about convection, and I think that this is hopefully a topic that's of interest to many of you in the audience. I think convection is a really universal phenomena that we find both fascinating and also interesting. And the kinds of models, fast forward a few hundred years from Newton, this is the kind of model that we want nowadays. This is our idea of an interpretable generalizable model, is the Lorentz 1963 model for chaotic convention. This is, most of us are familiar, this is what gives you the chaotic butterfly attractor. Notice I've added Fetter and Hamilton's names to this reference. I don't know how many of you have heard of this, but Ellen Fetter and Margaret Hamilton of the NASA fame were grad students with Lorentz and ran all of the codes and simulations he used to generate the data to build this model. So by modern standards, they would almost be co-authors on this famous paper. But the idea here is that this is a very complex PDE, kind of spatial temporal system, but large-scale patterns evolve that you can extract and that you can write down equations for. And when Lorentz did this, he extracted the x, y, and z variables by hand by projecting the Navier-Stokes equations, the governing equations, onto 3 hand-picked Fourier modes. We want to start to automate this process for our problems so that we don't need one kind of singular expert to guide the whole process, but we want to automate this model discovery process. And so in my lab, what we're doing is we're developing kind of automatic procedures to pull out nonlinear reduced order models from very complex physical systems that are physical by construction and are interpretable and generalizable. So let's say we took that same system, this Lorentz system, and let's say for now, we knew how to measure the system in those 3 spatial Fourier modes. We knew that the x, y, and z variables were important. In fact, Lorentz got that information from Saltzman before him. And I have time series of x, y, and z and their derivatives. Now, the simplest thing you might try to do is build a linear regression model that best fits x dot, y dot, and z dot in terms of the variables. This would give you a little 3x3 linear matrix, and this is what the dynamic mode decomposition does. But I don't think any of us really believe that with a 3x3 linear differential equation, we can capture the full complexity of the Lorentz system. So instead, what we do is we augment the right-hand side with all of the possible forms that the nonlinear function might take. So instead of just linear terms, I had quadratic, cubic, quintic nonlinearities on the right-hand side. And I can compute those gray columns from my measurement data, from the colorful columns. I can compute x squared from x, and so on and so forth. And now the trick is to find the fewest terms in that library of candidate nonlinearities that describe my x dot, my y dot, and my z dot dynamics. Now, 30 years ago, this would have been an impossible task. You would have needed a combinatorially expensive computation. This wouldn't have scaled with Moore's law. But if you are in the modern era with robust statistics, this is essentially a sparse regression like the lasso, or there's dozens of other ways of finding these sparse linear combinations. And when you do this, what you uncover is that the fewest terms needed to describe x dot, y dot, and z dot highlight the actual terms that were in the original nonlinear differential equation. So purely from measurement data, you can uncover both the structure and the parameters of a nonlinear reduced order model. Okay, so that's the pipeline that is kind of automating this model discovery process. And for the remainder of the talk, I'm going to walk you through vignettes of how we've applied this to very complex systems in fluid mechanics. If you're interested, we have open source code PyCindy, so you can kind of download this, try it out on your system too. Okay, so this would only be cute if we could apply it to Lorentz, but nothing more complicated. So now I'm going to show you how we do it for spatial temporal PDEs. So again, we're going to look at this flow cylinder at Reynolds number 100. And again, we know from past experience that there is a good coordinate system in which to represent these dynamics in a low order sense. And so in those 3 coordinates on the left, I get this simple differential equation on the right. If we project the governing equations, this is what Bernd Nowak did in his famous 2003 paper. Now, if we go to our Cindy algorithm and we try to learn these dynamics, we can essentially learn an identified system that has the same slow fast timescales, same quadratic nonlinearities, same basic symmetries of the original problem. Now, what I think is really nice about this sparse regression framework is that it's essentially built on linear regression. You do a least squares and then you sparsify. Then you do a least squares, then you sparsify. And when you do these least squares regressions, it's very easy to enforce known constraints. So Jean-Christophe Loiseau from Paris Tech, and I highly encourage you all to collaborate with someone from Paris, he very quickly realized that we were leaving a lot of information on the table. Our governing Navier-Stokes equations have symmetries, these skew symmetric quadratic terms that are necessary to enforce energy conservation. And so he wrote down a system of constraint equations that we could enforce at every step of our iterative sparsifying procedure. And so JC's models are sparse and conservative by construction. So that was the first innovation. The second innovation was, our Navier-Stokes equations have quadratic terms, but if we include higher order terms like cubic, quintic, septic, nonic, and so on, we actually can get rudimentary closure models for the high frequency stuff that we're leaving out of our truncated basis. And so if you compare what we see in the right column here is the industry standard best reduced order models before Cindy. So the white curve here is the ground truth from high fidelity simulations. These are basically the drag coefficients for these two fluids. And the yellow and blue are the best industry standard reduced order models with 3 modes and 7 modes from before. So they're qualitatively close, but they're quantitatively pretty far off. And when we add in this sparse nonlinear modeling procedure with our cubic nonlinearities or our symmetry constraints, we essentially nail both the transient rise time, the overshoot, and the steady state. So much more accurate models. And because they're sparse, you can actually write down the terms in the model with them like we would do classically in a textbook problem. And so what JC was able to do for the cylinder flow was rewrite our governing equations, our reduced order model down. And he showed that this model with these coefficients described that cylinder flow to that level of accuracy on the lower right. This is to date both the simplest and most accurate model for this fluid flow that has been written down. Okay, and so we found this model by sparsity constraints. You can also, you don't need the full flow field, so that's pretty prohibitive if you want to put this on a Boeing or an Airbus aircraft because they can't measure their whole wake behind them. So instead, we can also build these models based on more physical measurements. So for example, on this 3-cylinder configuration, we measure the lift and drag on those 3 cylinders, and we can build a reduced order sparse model in those coordinates that you see below. So we get a very, very faithful reconstruction of those coefficients. Okay, I want to go back to the thermal convection example. So we talked about the Lorentz model. We talked about how this is now identifiable if you know the right coordinate systems. I also want to point out that my colleague JC Loiseau, the same JC from earlier, applied this to this chaotic thermosiphon problem. So it's basically a hula hoop full of liquid where you heat the underside of it and it creates these chaotic convection cells that kind of chaotically switch from rotating counterclockwise to clockwise. And what JC was able to show is that with automatic feature extraction, he basically pulls out coherent structures by hand, he recovers an equation that is identical to the original Lorentz model. So the Lorentz model is somehow universal for these kinds of chaotic convection patterns, even if it's not in the standard kind of flat plate convection. And since then, we've started extending this with Yifei Guan and Igor Novoselov to more complex multi-coupled convection systems. So here is a chaotic electroconvection where instead of a 2-way coupling between fluid and thermal effects, we have a 3-way coupling between fluid flow, charge density, and electric field. And so essentially what we're able to do with our measurement data alone is extract low dimensional basis using essentially the proper orthogonal decomposition. I think they're called EOFs in climate. When we plot the evolution of the amplitudes of these time series as they evolve in time, you see these very beautiful symmetries in these mode coefficients. This is basically the amplitude of those modes as they evolve in time. A1 is the first mode, A2 is the second mode, and so on. And so there are these deep, deep symmetries in this equation because of the coupled physics. We can constrain our sparse model identification to enforce those symmetries. And what we get out is a low order kind of skeletal model that captures much of the same features of the original high dimensional simulation. And so a lot of this boils down, at least in my experience. So this is a big point about machine learning for dynamical systems and for physical sciences. We have so much extra information that the traditional machine learning community doesn't have. We know about symmetries and conservation laws, constraints. And when we bake those into our model identification machine learning tools, we get much, much better models with much less data. So for example, if I enforce these 5 symmetries, I can kill most of the candidate terms in my model, and it makes the identification much simpler and much better confidence intervals. Okay, so maybe the last thing I'll point out is that we've also applied this to Magneto hydrodynamics plasma simulations. So this is a SphereMac simulation that Alan Kaptanoglu is running. And again, you can pull out kind of this low dimensional feature basis using something like POD. And in the bottom, you can see this kind of low dimensional attractor where things are evolving. And based on physical constraints that you can derive from the partial differential equation, you can constrain your low order model to almost perfectly match the observed dynamics on those coherent structures, but much, much simpler description that you can actually write down and interpret. Okay, I think I'm running out of time here, and maybe I have like 1 minute left.
You have a couple of minutes.
Oh, I have a couple of minutes. Wonderful. Then I will. So this is the part I actually really wanted to show you, is this dominant balance, because I think this might be really relevant for this community. This is work by Jared Callahan. And again, I'm going to show you a fluids example, but I want you to think about your problem here. So we have this equation for the Reynolds average Navier-Stokes that we use for our aircraft. And you notice that it has a bunch of terms in the model. So what you can do is you can actually plot in time how big each of the terms is, and it looks something like this. Now for each of those space-time points, what you can do is you can plot a scatter plot of those space-time points in terms of the magnitude of each of those terms in the model. So you have a partial differential equation, you scatter plot all of your data in that equation space. And if you apply clustering algorithms, you see that these clusters start to form in the data, and different regions correspond to different active physics being turned on. And those active physics terms have names in my field, in the field of boundary layer physics. But you can also use this in systems where you don't know the answer, okay, to uncover different physical regimes with different balance laws. So for example, you can apply this to the boundary layer, laser optical propagation. We applied this to the fluid flow in the Gulf of Mexico, bursting neuron equations, and recently we've applied this to combustion problems. But we've been thinking forever that the kind of geophysical community is actually the perfect user base for this to figure out what these different dominant balance regimes are. Okay, so now I'm actually going to end my talk. I'd be happy to take questions, and thank you so much for the invitation to share our work with you. Thanks.